I'm Alex Mitrevski, PhD student at Hochschule Bonn-Rhein-Sieg and RWTH Aachen University in Germany. Today I will present work done jointly with my advisors, Professor Plöger and Professor Lakemeyer, with the title Robot Action Diagnosis and Experience Correction by Falsifying Parameterized Execution Models. Our work is centered around the topic of robot execution failures, such that we want to equip robots with an ability to learn from their own failures in an intelligent way, similar to how people reason about failures so that they can be subsequently avoided. To learn from failures, a robot needs to have an ability to diagnose failures, namely it should find out what the reasons for a failure are and then find out a way to correct this failure. Diagnosis and failure correction are the two aspects we deal with in this paper. In the literature, there are different ways in which failures can be diagnosed. These can roughly be classified as model-based, in which a detailed system model is created and then used to produce likely failure reasons, and data-driven, where a diagnosis model is learned rather than specified manually. The method we present in this paper falls somewhere in between, such that we propose algorithms for diagnosis and experience correction that are motivated by work on counterfactual reasoning on the one hand and qualitative modeling on the other hand. This paper builds on our prior work at IROS 2020. There we proposed a representation based on which the process of robot action execution is governed by both relational execution constraints as well as a model whose objective is to predict the robot's execution success for a given action parameterization. An action execution model is acquired using experiences with sparse reward. Action execution parameters are then sampled from the model using rejection sampling. Here we present methods that use this representation for fault diagnosis and subsequent experience correction. First, given action parameters that have led to a failure, diagnosis is performed by using the model of relational constraints in order to find alternative parameters where some of the execution constraints are violated. A violation of the relational model represents a likely diagnosis candidate. This information is then used to propose a correction to the parameters that is more likely to lead to successful execution. It is important to mention that our methods need to be used in conjunction with an anomaly detection method. The problem of detecting anomalies is not in the scope of this paper. We illustrate our method in the context of handle grasping. Here, grasping the handle is the action of interest, parameterized by the relative position between the robot's end effector and the center of the handle. One possible failure here is missing the handle because of an incorrect handle pose estimate, which leads to a grasping position that is slightly to the left and above the handle, as shown in this figure. If this failure is correctly diagnosed, it can be corrected by moving the robot's hand towards the right and slightly below of the original position. We will now briefly look at the ideas behind the diagnosis and experience correction algorithms. The diagnosis algorithm performs a local parameter search around the parameters that originally led to an execution failure, denoted here by X. The objective is to find a parameterization that violates at least one of the relational constraints of the action. For instance, if the handle grasping position is moved a little more to the left, the relation not left of the handle is likely to be violated even under an incorrectly estimated handle pose. This search is performed by sampling a predefined number of alternative parameterizations from a Gaussian distribution that is centered at the original parameters and with a diagonal covariance matrix sigma that defines the search region size. The search stops if relation violations that do not contradict each other are found within the maximum number of samples Kmax. Otherwise, the region is expanded by a predefined ratio R and the sampling process is repeated. The idea of a consecutively increasing search region is similar to that of iterative deepening tree search, but applied here for a continuous parameter space. The result of the diagnosis algorithm is a set of relations that are violated when a local perturbation of the action parameters is undertaken. In the handle grasping example, these would be that the robot's hand is to the left of and above the handle. These violations may be produced by one or more samples within a search region. Now, as mentioned before, in addition to identifying relation violations, the algorithm finds an alternative parameterization that causes those violations so that the robot can then correct the execution. This is achieved by combining all samples responsible for finding the relation violations by a simple summation. This summation is based on the assumption that each relation of interest is governed by a single action parameter. In our example, a relation such as left off is only governed by the y position of the robot's hand with respect to the handle, while a relation such as above is governed by the y position. Once a violation of the execution relations is found, and we have an alternative parameterization that leads to that violation, the next step is to suggest a correction of the execution parameters that is more likely to lead to a successful action execution. We achieve this by moving the parameters x that originally led to a failure away from the direction in which the relation violation was identified. We particularly sample an alternative parameterization from a gamma distribution, such that we set the parameters of the distribution to discourage parameter updates that are too far away from the original parameters x, as making a too large step may lead to new and unforeseen failures. The correction algorithm generates multiple samples from the gamma distribution. These are then evaluated by the success prediction model, and the parameters with the highest predicted success are taken to represent the parameter correction x star. In this video, we show the diagnosis and experience correction algorithms in action. We first see our robot, a Toyota HSR, attempt to grasp a handle in our lab, but due to an incorrect estimate of the handle's size, the robot grasps a bit too much to the left of the handle and slightly above it. The diagnosis process starts centered at the original failed parameterization, such that multiple samples are generated within the search region, as is shown here. If a set of relations that don't contradict each other is not found, the search is continued within a larger search region. For correction, we identify the direction in which the parameters were moved for the violation to be found, and then sample new parameters away from that direction. The parameters that maximize the available success prediction model are taken to represent a correction of the original failed parameterization. In the experimental analysis of the diagnosis and experience correction algorithms, we investigated two main aspects. First, we analyzed how the performance of the diagnosis algorithm is affected by its main parameters, namely the size of the initial search region sigma, the number of parameters per region kmax, and the region expansion ratio r. Second, we looked at whether learning a success prediction model using the corrected experiences, together with their failed counterparts, would allow the robot to perform the handle grasping action successfully. For the analysis, we repeated the handle grasping action 100 times using an execution policy that generates random grasping points within the bounding box of the handle. Of these, 84 executions failed, such that for analyzing the performance of the diagnosis algorithm, we manually annotated the ground truth diagnosis. Our dataset and implementation of the algorithms are available on the links shown on this slide. To analyze the effect of the size of the initial sigma, we ran our algorithm with ratios of an anchor size, which is set to 10% of the average bounding box size over all trials, and kept kmax and r fixed. The results show that this parameter has a significant effect on the performance of the algorithm, such that increasing the size allows diagnosing the failures, but at some point the performance saturates, and further increase only leads to a higher number of false positive diagnoses. A similar analysis was performed for the region expansion ratio r, where we kept the initial sigma and kmax fixed. The results here show that this parameter does not have a significant effect on the algorithm. However, we hypothesized that the effects of the parameter may be more prominent for a very small initial search region and a large region expansion ratio. Finally, we analyzed how the number of samples kmax generated per search region affects the identified diagnosis. As the results show, this parameter has a similar effect as the initial search region size. In particular, increasing the number of samples allows diagnosing more of the failures, but the effect saturates, and beyond a certain value, only the number of false positive diagnoses increases. In our final experiment, we used failed experiences together with corrections suggested by our algorithm, which can be seen as synthetic learning experiences, to learn a new success prediction model. We then repeated the grasping action 60 times by sampling from the new prediction model, such that we compared two different values of the gamma distribution parameter that controls the size of the corrective updates. According to the results, the success of the robot is reasonable even though the prediction model was only learned from synthetic successful experiences, but the smaller corrections lead to better results. In conclusion, we showed that our diagnosis and experience correction algorithms were able to identify most execution failures, at least in the context of the handle grasping use case, such that the diagnosis algorithm is affected significantly by the size of the initial search region and the number of samples per region. We also showed that learning a success prediction model from corrected parameters, which can be seen as synthetic successful executions, leads to moderate execution success, but the success is affected by the magnitude of the corrective step. Some ideas for future work are including synthetic experiences into an existing execution model, which would represent true learning from failures, as well as investigating how our algorithms generalize to failures that are not of spatial nature. For instance, failures due to applying a high force while grasping. It would also be worthwhile to investigate how to relax the assumption about the surjective mapping between relations and action parameters, and to consider a simple learning method so that relations relevant for a given action are automatically extracted rather than manually specified. Finally, it might be useful to investigate strategies to identify the initial search region sigma automatically rather than using a heuristic value, which is what we have done here. For more details, please take a look at our paper. Thank you.